Good morning, here yet again for another session of CENG 3325 Structural Analysis. Alright, so we're going to start with this video off by looking at the topic of load path. So we've talked about definitions of loads, we've talked about types of loads, we've talked about how we contain and analyze and control for risk. And next I want to illustrate or discuss the concept of load path in structures. So load path. When I say load path, what does that conjure up in your mind? What do you think of when you think of load path? Load path.
The way the force travels.
The way the force travels, exactly, the way force travels. Load path describes the way a force travels through a structure. So again, we could describe this as the method or the way, probably not method, but the way load travels or is gathered through a structure. Or is gathered in a structure. So ultimately, at least in a civil engineering application, where do the loads ultimately always end up?
The reactions.
And the reaction's true, but in terms of buildings, like actual physical structures, what do those reactions mean? The foundation, yes. Ultimately, all the loads of a structure end up in the foundation. They're always ultimately going to end up in the earth, delivered to the soil. So for buildings and for structures, now if you're designing airplanes or something, this may be a little bit different, but for any kind of civil engineering application, ultimately the loads will have to find their way to the soil. The loads must find their way to the soil. So we're going to look at this from the point of view of both vertical loads and lateral loads. They must find their way to both the foundation and then the soil. And this is true for both lateral and vertical. So I want to trace through load path for both vertical and lateral. First of all, when I say that vertical and lateral, I want to discuss examples of these. Vertical loads, examples of vertical loads. This would be things like dead load. Dead, most live load, some wind, seismic, some wind, especially like roof wind load, some seismic, etc. And then for lateral loads or horizontal loads, we could have many different ones, but the primary ones are going to be, let's see, mainly wind, at least here in Houston. Then if you're in a seismic region, seismic load will be your dominant lateral load. And then you can also have soil pressure in some cases. If you have, say, a retaining wall. So if you had a hillside, for example, let's say you have a hillside like this and you want to build a lot on this hillside. Well, one thing you can do is you can sort of carve out the hillside, carve out a portion of that hillside, and build a building or a structure here. But to retain this, to keep the slope from reestablishing itself, you build a retaining wall, and then you fill this in with something. And so your retaining wall here would have both its own self-weight, but also would have the lateral and pressure load and overturning moment from the soil here. So pressures can be a lateral load. And also if you had something that was like a hydroelectric dam or just a dam in general, the lateral load from water could be another lateral load, the hydrostatic load from water. Okay, all of these are lateral loads. Now, next I'd like to look at how we consider load path for each of these. And this is just going to be an example, or this is going to be a general discussion. Load paths can be quite complex, but I just want to discuss the theory very briefly. I'll give some examples. vertical load path. Oh, I'm missing a D. Okay, vertical load path. So let's talk about live load. Let's look at say live load. How is live load carried? Vertical live load carried. Well, we of course know that live load is the combination of really everything in a structure that moves around, that can be picked up and moved around, that will occupy different places at different times. In this classroom, all of the live load is yourself, myself, the tables, the chairs, all of our belongings, coats and backpacks and things like that. All of that stuff is live load. So where does the live load first go? So live load is first generated by everything in here that's movable. But then where does that live load first go? What's the first element in this room that gathers up live load?
Carpet.
We could say the carpet, yes. I would almost consider the carpet itself to be live load. But I would say the floor, particularly the floor slab. The floor system is what first captures the live load. And this floor system could be any number of things. If you were in a single-family home, typically this would be plywood. You would have plywood flooring, plywood decking. So the floor system. Again, this could be either plywood. Now, this building is definitely does not have plywood floor, or it could be a concrete floor slab. A concrete floor slab. So maybe I can number these. So first it goes to the floor system, whether a plywood or a concrete floor slab. Then it's going to go to something like a series of beams, very typical. Beams, which support the load, which support the floor slab. Then from there, the load will pass to girders, which are larger beams that carry beam end forces. And then 4, it would go to columns. And then 5, the foundation. And that's the basic idea of load path. Every bit of load must be passed on to the member after it. So, in turn, the load increases as you go down. A given patch of floor slab only needs to carry a very small amount of load. The beams that attach to the floor slab will carry higher load. The girders that carry those will be even higher, etc., etc. So loads combine and increase. And with this, I probably need to discuss floor systems. So I'd like to lay out what we mean by beams and girders, and also introduce the idea of tributary area, in case you're not familiar. The idea of tributary area. Okay. So let us look at floor systems. I generally define beams. So first of all, I want to distinguish between beams and girders. In common parlance, we kind of use these terms independently, or interchangeably, I should say. Usually some people just say beams and girders, they'll use one, half dozen the other. In common parlance, these are interchangeable. But in engineering or in structural engineering, these are not interchangeable. Beams and girders have specific definitions. A beam is something that directly gathers area loads. Directly gathers area loads. And a girder would be a horizontal member that supports beams. That supports beams. So for example, let's say we had a single column, let's look at a single column bay here, a single bay of a floor slab, and I'm going to have, let's say, 4 columns here, and then I want to show some beams and girders. So maybe I'll do this here. These would be girders, maybe in this direction, if I can manage to draw a straight line. here. So these would be my girders. Although they wouldn't have, they could run just as well in this direction, or you could actually have girders in two directions as well, depending on how you set up your flooring system. And then maybe you have beams running in the other direction. Running in the other direction. Like this. So, for example, if I were to draw the free body diagrams or the loading diagrams of each of these, the beams, let me maybe draw a beam loading diagram and then a girder loading diagram. A girder loading diagram. So here, the beam would be directly supporting area load. It'd be going something like this. There might be a uniform load all the way across it. A uniform load. And this would be the uniform load from live load, dead load, usually maybe like a 1.2 dead plus 1.6 live, that sort of thing. It'd be the distributed load from the area loads here. Meanwhile, and it would have, maybe it could be simply supported, something like this. Or it could be fixed, I suppose, but it would be supported at the ends. Then a girder is going to have a series of point loads on it. The main loads it's going to be supporting. Now, yes, it would have some distributed load, its own self-weight, but the primary loads for the girder would be the point loads, the end reactions from these beams. So in other words, this force here would be the same as this force here. This force here would be the same as this force here. So the girder, the beams will gather up the load from the floor slab, and then they will distribute it to the girders via end reactions. So this is the idea of load path. We can see how load is being gathered. It starts as an entire area load, like a certain number of pounds per square foot, 100 PSF, 80 PSF, 200 PSF, whatever it may be. Then it gets gathered via tributary areas onto our beams here, and then via reactions, end reactions, it gets deposited into the girders here. And then in turn, the girder is deposited into the columns, and the columns take it down to the foundation. Questions on that?
That's what I have. So, like, in residential construction, would the girder be like the ceiling joist?
Exactly, yes. In residential construction, a girder would, a beam would be more like the ceiling joist.
Okay.
A beam would be more like a ceiling joist.
And girder is like the glue lamb that sits on it?
Yes, in residential construction, a good analogy for this would be the beams would be very much like ceiling or floor joists, and the beams would be very large glulims that the joists are laying on top of.
So if I did a vaulted ceiling, is it still a beam?
If you do a vaulted ceiling, the question is if you do a vaulted ceiling, is it still a beam?
Is it still carrying the load?
There would still be it would be a combination of beam and column at that point. So, but yes, there would be bending in there, but it would also be substantial axial force. So a vaulted ceiling, the members there, we refer to those as beam columns because they have both axial force and moment present in them. Okay, next I'd like to discuss one-way versus two-way loading. What I have drawn here is a one-way flooring system. So let's discuss one-way versus two-way loading. One-way versus two-way loading. So in one-way loading, the beams, or I should say the elements in one-way loading, the members that will gather just area loads. Area loads run in only one direction. Run in only one direction. Oh. In only one direction. And so because of that, you're going to use rectangular, you're going to divide your area up by rectangles. So but essentially this is rectangular load distribution. Rectangular load distribution. For example, like we had last time, or like we had in the previous slide, if I have a girder here and a girder here, and maybe a beam here, and a beam here. If I want to calculate the amount of load on this beam, on one of these beams, how do I do that? Well, we do it via basically dividing the slab up into tributary areas. So usually what I'll do is we usually use the midpoint. So I might say that, okay, well, this midpoint here, everything above this midline goes to this beam up here. Everything below this midline goes to this beam here. Same thing here. Everything above this line goes to this beam here. Everything below this line goes to this beam here. We're dividing it up by rectangular tributary areas. And so this beam is carrying this entire rectangular tributary area. So this is a rectangular tributary area. Everything in this purple rectangle will end up on the center beam. Everything on this, or under this purple rectangle ends up on the center beam. And what do we mean by this? Well, again, all of this is going to be based on the principle that load will generally take, at least for vertical load, load will generally take the shortest path. The assumption here is that load will generally take the shortest path. So if this bit of floor slab needs to be supported, if a given bit of floor slab, a given bit of live load, a given bit of floor dead load, when it needs to be supported, it's going to pass to the closest beam. And again, for one-way loading, basically we're saying there are no beams or girders running in this direction, or even though there are girders running in the vertical direction here, those girders are not carrying any of the floor slab load directly. Rather, all of that distributed load is being gathered by the beam, and then the beam is passing the load to the girder. So, but that's just a design assumption. And the point of this is that when you then design your girder when you design your beam, you will use this loading to create your shear and bending moment diagram. You get your load diagram, then based on that you get your shear and bending moment diagram, then you can design select actual sections to carry those loads. That's one-way loading. What about two-way loading? Let's consider two-way loading. Let us consider two-way loading. So here, major distributed load gathering elements travel in both directions. Are present in two directions. In both directions. So for example, imagine I did something like this. Let's say I have my columns again. And this time, instead of girders traveling in just one direction, I'm going to put big girders in both directions. So I'll do that here. Have major girders going like this. In between the columns. Same here. And here. And then I have beams running in two different directions. So something like this. Although hopefully your beams are a bit straighter than I've drawn here.
So those squares are columns?
Yes, these are columns here. The black squares are columns, yes. So how does load, if I have beams running in two different directions, so I basically have a grid type pattern here. If I have something like this, how does load get divided? Well, oftentimes 2A loading is also sometimes referred to as trapezoidal loading. That's another term for this. Or trapezoidal area loading. And the reason for this, again, it's going to come down to sending load to the closest location. So for example, if I look at this dot here, if I look at this location right here, the closest bit of beam would be right here. If I look right here, the closest bit of beam is right here. If I look right here, the closest bit of beam is right here. Load will tend to go to the closest location. And so, if I were to divide this up, if I were to draw up the divided areas, something like this, this would end up being divided by, this particular thing would end up being divided by triangles. So, in other words, this triangle here, everything in this triangle here would end up on this bit of beam here. Everything in this triangle here would end up on this thing here. Everything in this thing here would end up on this thing here, etc. The load gets divided triangularly. At least if the thing, at least if the load, or if the bay here, if the shape, if floor slab, if I should say the rectangle, or if the boundaries between beams are reasonably square, like I would say these are, can assume triangular loading. Triangular sections, or triangular loading. Triangular loading. I would say if the width is maybe if length is maybe twice the width, that's when you need to consider rectangular loadings, or sorry, trapezoidal loadings. If width more than twice length, or vice versa, if one dimension more than 2x than another, twice another, really need to consider. And there may be a better, if you want to do this really accurately, you would always use trapezoidal loadings if it's not a square. But anyway, really need to use trapezoidal, but you especially need to use trapezoidal loadings if you have one dimension twice another. Trapezoidal loadings. And let me show what I mean by this. So if I have a beam that is a square, or not a beam that is a square, but if the boundaries between beams make a very square shape, it's reasonable to assume this kind of triangular distribution. But what if I have beams that are laid out in more of a rectangle? What if I have 2A beams and the boundaries are more like this? See, if I assume that I have triangular loading, I would end up with something like this. If I assume triangular loading, I would end up with something like this. But let's look at this piece right here. Again, we said that load will tend to go to the closest location. Here, though, let's look at this. If there is so if we assume triangular loading, this piece of slab right here, this piece of live load, dead load right here, is it really going to go all the way over here? Is that the closest beam at that point? No, the closest beam would be here or here. Loading will tend to go to the closest location. So instead, what we tend to do for things that are rectangular is more of a trapezoidal loading. What do I mean by that? What I mean by that is if you want to divide a rectangle into trapezoidal loadings, you do the following. You start by going out at a 45-degree line from the corners. So you go 45 degrees out from the corners. Same here. And you go out until they meet up. This is 45, same here. 45, and 45. And then once the two 45-degree lines meet, then you have a line that goes down the center. So you have two triangles on the ends that go to the narrow ends. So this triangle will go to this beam, this triangle will go to this beam, and then this trapezoid and this trapezoid will end up going to the beam at the top and the bottom. And the whole idea of this is once you have this area, you can then multiply by the area loads to transform those into loads per foot, pounds per foot, kips per foot, that sort of thing. So maybe I could run through a brief example here for, say, a one-way loading. I know some students sometimes have trouble with this, especially when I just go through the theory here, but sometimes it helps to put some numbers to these things. So let's look at vertical tributary area example. Maybe I'll do that on the next slide. Tributary area example. Okay, so let's say we did something like this. Let's say there is on a floor system, there is a factored ultimate load. So this would include live and dead, for example. A factored ultimate load of 120 pounds per square foot with a layout as below. As below. So let's say we had I'll do the same kind of beam column type thing. And when I draw this out, realize that I'm just drawing out one particular grid. Like there would actually be more columns here, more columns here, more columns here, just depending on how big the building actually was. But I'll just go ahead and draw out one here. Let's say for some reason it was just a single, this is the whole structure. Like maybe it was just literally just a single 4 columns connected by girders and then some beams. Very unusual structure, but let's just say we had something like that. So we have girders here. I'm going to go ahead and put dimensions on this. And then beams, I'll go ahead and keep doing my purple and gold, why not? There's a small little town outside of Des Moines, Iowa called Waukee, Iowa, where I grew up as a kid, and the high school team colors were purple and gold. So anyway, that has nothing to do with structural analysis. Okay, so let's have some dimensions on here. Let's say this is, I don't know, maybe let's make this 12 feet. I'll try to keep from reusing the same dimensions. And then let's say this is not to scale, but let's say this is at, I don't know, what could each of these be at? Definitely not to scale, that's what they're definitely not. Let's see, 4 feet would be 12 feet, 5 feet. Let's say this is, actually, wait, does that look right? Yeah. So you want 4, so maybe 4 feet, 4 feet. 4 feet. That's, oops, derp. 4 feet and 4 feet. So these beams are 12 feet long and they're positioned 4 feet on center from the columns or along the girder. So let's see, and this whole thing, let's say, and I'll go ahead and put some secondary beams here. I'll go ahead and say there's also a beam running directly between the columns. And these aren't going to carry, these aren't girders, they're not going to carry load from other beams. They're just going to carry distributed load directly to the columns. So let me call this one column AA. Maybe this is going to be column AA, and this would be column BB. Okay, so what I want to do is I'm tasking us with draw the load diagram on beam AA, BB, and one of the beams. For now, ignore member self-weight. So I'm going to ignore member self-weight for now. That would be added as just part of the line load. That would just be added as part of the beam line load. Okay, so let's consider this for a moment. Now, let's look at beam AA, for example. Beam AA has a tributary area 2 feet wide. Beam AA is going to have a tributary area 2 feet wide. Again, because I'm saying that this is a very unusual structure and that it's not, I'm making this really simple, but in turn very unusual, in the fact that normally you'd have more columns over here, you'd have more columns over here. This grid of columns would keep extending. But I'm just going to say for simplicity that this is just a simple structure with only one bay like this. And so there are only 4 columns altogether. So in terms of tributary area, this beam is going to support this strip here. And I know that this is not going to be a one-way loading system because I have beams working in only one direction. Actually, I probably should be told to assume one-way loading, even. That'd probably be good for a problem like this. One-way loading. So this beam here, solution. Well, AA is going to support is going to have a width of 2 feet. So that means the W on it is going to be 2 feet times 120 PSF PSF, and that will come to 240 pounds per foot. So that means beam AA will look like this. We could assume simply supported depending on the actual support conditions, but it would be something like this with a uniform load of 240 pounds per foot. Again, I just multiplied the width of the strip, the width of the tributary area, times the magnitude of it, times the distributed area magnitude of it, the distributed load of it, to basically 120 pounds per foot times the strip width of 2 feet. So this would be 240 pounds per foot. And if I get out a calculator, I'm going to pull out my calculator here. I want to get the reactions here because I want to be able to do that on the columns, on the girders. Let's see, 240 I'm going to get the total load, so times 12, and then divided by 2. I will have reactions here of 1,440 pounds and 1,440 pounds. All right, questions on that so far? Any questions so far? Yeah. Basically, I'm assuming that it's connected via simply supported. It doesn't have to be. We could have rigid supports, and that would change the bending moment there, and et cetera. And it would also put some end moments. But right now, I'm keeping it simple and just assuming everything's simply supported. But yeah, good question. Okay, now I want to get beam BB. And this one's going to be very similar to the previous one. It's just going to be, it's the exact same process, except now the width of the tributary area is going to be 4 feet instead of 2 feet because it gets 2 feet on this side and 2 feet on this side. So the W here for this particular one would be 4 feet times 120 pounds per square foot, and that would equal 480 pounds per foot. So that would be my distributed area, my distributed load or my line load W. And so the loading diagram for this would look like this. If I go and get my red pen here, it would look like this. This would be 480 pounds per foot. And because this thing is 12 feet long, if I multiply this by 12 and divide by 2, I will find that the reactions here, assuming pin supports, would be 2,880 pounds. 2,880 pounds. Yes.
How do you get 4 feet?
How did I get the 4 feet? Okay, tributary area. Again, it comes down to tributary area. You have a beam. You have a beam here. There's another beam 4 feet away. And there's another beam 4 feet from it. Load passes to the closest location. So, essentially, everything on the midpoint line between the two beams, everything above it goes to this beam. Everything below that midpoint line goes to this beam. Same thing here. I draw the midpoint line between the two beams. Everything above this midpoint line will go to this beam. Everything below this midpoint line will go to this beam. And the combined width of both of these is 4 feet. Does that make sense? Okay, does that make sense? Okay. Tributary area. Okay. Then finally, let us consider the girder. Consider the girder. And this would just be a series of point loads. Now, it wasn't necessarily stated, but I have a couple things I could assume on this. I could assume the beam, depending on how this is connected, the load would be different. Like, we could assume that the girder here goes on top of the column, and then this beam rests on top of this column, and then this beam rests on top of that girder, or we could assume that this beam distributes the load directly to the column. I'm just going to go ahead and assume that beam, the top and the edge beams, distribute the load directly to the columns. For here, I will assume, but you could design it either way. Top and bottom beam. Beam distribute their load directly to the girder, directly to the column, bypassing the girder. Distribute load or deliver load directly to column, bypassing girder. So that means my girder, this girder here, will not be supporting the end reactions from this beam and this beam. In other words, the 1440 we found earlier, that's not going to be supported by this girder here. That load is going directly to the columns. So, but then I could draw the load diagram for this thing. And so it would look like this. I would basically have 3 point loads, each of which would be equal to the reactions from the previous beam BB. So 2,880, 2,880, and 2,880. And then if I go and multiply that by 3/2, or multiply by 3 divided by 2, I would get 4,320. 4,320 pounds here. And that would be our basic reactions there. Now, what if I wanted to find, oh yes?
Would the distance between the column and the first beam be equal to how much? Would it be 4 or 2?
The distance between what?
The column and the first beam.
0. It's connecting to it, isn't it? What are you asking exactly?
It's connecting to the center of the column? Or
Yes. Center of the column, center line of the column. I mean, good. You're looking at the column. You're looking at we're looking down. This is okay. So I'm not sure what you're asking
Not,
exactly.
not the top one, the second one.
This is not a column, this is a girder. This is, in black we have the columns. Okay.
Distance between the column and the first beam.
Oh, you mean the center line of here to the center line of here. As the drawing says, it's 4 feet right here. It's 4 feet from the center of the column to the center line of this beam. Okay? All right. Okay, now what if I wanted to know the total load on the columns? Well, the columns, if we want to know the total load on each column, a very easy way to do this is you could do this two ways. One, you could add up the reactions from the beam, from this beam and from the girder, or two, you could actually use a tributary area approach in the column directly. You could just say, this column will carry this entire area load, that's the load on the column, or you could add up the end reactions from here and here. In fact, let's go ahead and do that and show that they should be the same. Calculate column load. And let's do this two ways. Here. Let's see. One, end reactions. Try two methods. Two different methods. One via end reactions. Basically, each column carries an end reaction from a beam AA plus the girder end reaction. So the P then would be a combination of this point load here and this point load here. So 1440 plus 4,320. And that will come to 5,760 pounds. So two tributary areas in this particular problem, each column should carry 1/4 of the total area load. Let's see if we did the math right, which is not always guaranteed. So the total area load, this whole bay, is going to be 12 feet by 16 feet. So total load would be 12 feet times 16 feet times our load of 120 pounds per square foot, and then divided by 4. 12 times 16 times 120 divided by 4. And what do you know? We get the same value, 5,760 pounds. So we see here, I love this example because this illustrates that tributary areas, load path, etc., they don't change the total load that's present in the system. All they do is they gather it. All they do is show how it gathers up. We can look at this from the point of view of total areas. We can look at this from the point of view of end reactions. But it's going to be, if you do it right, you should produce the same results. So you could actually design your columns like this as well. You can just say, you don't actually have to calculate the end reactions in order to calculate your column loads. Rather, you could just say, okay, this column is going to carry all the live load from the boundaries between the columns. So you could basically use a tributary approach just like what we did with beams. You could say this region here would be carried by this column. This region here would be carried by this column. You can use a tributary area approach. Okay, questions on that? Now that's a lot, maybe some new material, but once you get the hang of it, it's not too bad. Any questions on this basic one-way loading for tributary areas? Huh? Okay. All right, so next, maybe I'll look at a two-way loading. Again, still vertical loading. Two-way loading. maybe a brief numerical example. So let's say we had something like this. Let's say we have, consider a beam, consider the layout of 4 beams below. Let's say this was 20 feet. I'll draw the beams first. Let's say this is line 1, column line 1, 2, 2, and then A and B. B and B. And let's say this is 20 feet, and let's make this 10 feet. And let's say the factored ultimate distributed load is 100 PSF. Find the load diagrams of beams AA and 1-1. Find the load diagrams for beam AA and 1-1, assuming two-way loading. Assuming two-way loading. So we're going to need to divide this thing up into triangles and trapezoids. We're going to need to divide this thing up into triangles and trapezoids, two-way loading. Unlike the previous case where we only had beams running in one direction, we now have beams running in 2 directions, and so we need to consider two-way loading. Okay, so remember how I said it's going to come up at a 45-degree angle? Well, basically what that means is we have an isosceles triangle on the narrow end. So let's consider that. Maybe I'll do that on the next slide here. Okay. So again, we're going to divide this up into, we'll have a trapezoid running along the long end and a triangle running along the narrow end. So let's look at how we can divide this. So this is 10 feet and this is 20 feet. And I know that my my dividing line should start at the corners and go out at 45-degree angles. So sometimes you have to play a bit with the trigonometry. And this is 45 and 45. However, I know that these things that this line, just by basic symmetry, this has to meet up at 5 feet. And this would be at 5 feet. And then because this is a right isosceles triangle, this would be 5 feet. This would be 5 feet here. The same thing here. In other words, I'll have a triangle that is 5 feet on both legs. And then my trapezoidal region will go like this. Will be 10 feet long. So not necessarily symmetric. And this would be 10 feet long here. Or if I maybe draw this out a little better on a different rectangle, it would look something like this perhaps. I'm going to have a trapezoid like this, like this, like this, and like this, where this is 10 feet long, and let's say this is 5 feet long here. So the whole thing though is, of course, what I really want is, that's nice if I have the tributary areas, but what I really need though is I need a way of turning this into actual loads. And we know to get loads, to get distributed loads, to get line loads, W's, for load diagrams, we multiply the length of the strip. Again, let me just write this out maybe. To go from area load to line load, multiplied by the width of the tributary area at that location. By the width of the tributary area. So let me go ahead and get column, maybe, beam 1, 1 first. So let's get a load diagram for beam 1, 1. Now, looking at this, it's going to have some sort of triangular loading. Again, I'm just going to keep it simple and assume simply supported. But it's going to have some sort of triangular loading. And the reason for this is right at the edge, it has the width of its tributary area is what? Right at the corner, what is the width of beam 1, 1's tributary area? 0, exactly. And right at the middle, it's going to be 5 feet. So the value of the peak then is going to be 5 feet times 100 PSF. And PS, think of the units here. Pounds per square foot times feet, that comes to units of 500 pounds per foot. And it's going to start from 0, and then it's going to increase to the maximum of 500 pounds per foot. Like this. And it will have a width of 10 feet. Of 10 feet. And looking at this here, in the trapezoidal section for beam, say, AA here, it's also going to have the same peak value. Because look, it's going to have the same maximum width of 10 feet. It's going to have the same exact maximum width of 10 feet. And I guess we could get the reactions if we wanted to, if we want to be nice and consistent, or thorough, we could say. That would just be 1/2 base times height divided by 2. So the total load on that thing is 500 times 10 over 2, which would be 2,500, and then divided by 2 would be 1,250 pounds. And 1,250 pounds. Then I'd like to also get beam AA. Again, that is the long one here. And it's going to have the same peak value, but now it's going to be trapezoidal instead of triangular. So I would have my beam here. And then I would have a trapezoidal distribution like this. Same peak though. Like this. And the peak would be, again, 500 pounds per foot. Now, it's not necessarily always going to be the same, but in this case, the reason it's the same is because we have the same width, same maximum width here and here, the same maximum width. But then we'd also want to have the dimensions on here. This would be 5 feet, 5 feet, and 10 feet, so this is completely not to scale, but that's okay. This is the exact opposite of to scale. So that would be 5 feet, 10 feet, and 5 feet. And I might like to get the reactions, the end reactions if I want those. So let's see. Well, I could treat this as, essentially I could just treat this as 500 pounds per foot times a width of 15 feet. Or we could average the bases or something like that, the width of the bases. Well, actually, you can't do that exactly. So I'll just be nice and simple and say, okay, 1/2 base times height 0.5 times 5 times 500, and then multiply by 2 and divide by 2. Yeah, that makes sense. So that's 1250, and then 500 times 10. So 5,000, and then let's see again. But 500 times that is 2,500. So we have 7,500 pounds total. 7,500 over 2, and I believe we would have end reactions, if I math that correctly, of 3,750 pounds and 3,750 pounds. Now note on this, so that those are our basic tributary areas. Those would be the basic loads for, say, live load and dead load of floor slab applied to these beams. Now, I'm definitely leaving some stuff out, like something that is not shown on here. A major thing would be like the self-weight of the beams. So I would need to actually, if we were doing this in design, we would also need the self-weight of the beams. So instead of being a trapezoid that goes to 0 at the end, if the thing was, for example, say the beam weighed 10 pounds per foot, well, you would have a middle value of 510 pounds per foot. At the edge, it wouldn't go to 0, but it would go to 10 pounds per foot. You would have self-weight as well. But this is the basic idea of two-way loading for vertical loads. Questions on this? Fun, huh? Loads of fun. Okay. Next, I'd like to look at the process of load path for lateral loads. And in particular, I'd like to look at the example of wind loading. Oh. Let us consider load path for lateral loads, and in particular, wind loading. For seismic, it's a bit more complex, and I don't necessarily want to work through a load path for that one. It's a bit more complex because of the nature of inertia and such like that, seismic inertia and how loads distribute through structures that way. But for wind, it's a lot easier to understand. So let's look at load path, lateral load, wind. Wind. So, where is wind first applied to? Generally, wind is first applied to the outer cladding of a building. You have the wind. The air is moving. It's gonna brush up against the side of the building. It's gonna collide with the side of the building, and through a mixture of friction and inertial forces, it's going to generate a force against the side of the building, and it is applied to the building cladding. Whatever your outer cladding material is, this could be the glass of windows, it could be siding if it's a house, it could be brickwork, it could be any outer cladding, any outer surface, anything the building is actually, anything that the outer surface of the building is made of. It first is applied to the cladding. Then, usually it would be applied typically then to the floor slabs to which the cladding is affixed. Or beams to which cladding is affixed. Or I can just say attached. Then it will go to the columns. Then it will go to the foundation. So I can draw this out. So now we're going to look at a building. Instead of looking at it in plan view, we're going to look at it in elevation view. So let's say you have your columns here, series of columns. Maybe the ground is here. And then we have a floor slab here. And you could consider the floor slab directly distributing lateral load to columns, or you could consider it doing it via beams. But let's say this is a simple 2-story building. Big old thick concrete and floor and roof slab. So what's going to happen is, let's say there will also be some outer cladding on here. Let's say we have glass, for example. Let's say we have a big pane of glass in a window frame here. That glass is not strong enough to carry load all the way to the foundation. It's not meant to do that. Rather, you're first going to have wind load that's applied to the outer material. It could be glass, again, it could be brick, could be what have you. And so this is going to then, it gets applied to a plane of glass, it gets applied to a patch of brick, whatever it may be. Then this is going to distribute it to this slab and this slab. But then this floor slab is going to distribute it to all the columns. And usually it just doesn't end up at the closest column. If that were the case, no building would be able to stand up against wind. Rather, it gets distributed across all columns in a line, usually. If you assume, this is referred to as diaphragm action. We'll talk about that later in the semester. But basically, the floor slab, this big heavy floor slab, this big thick strong floor slab, then distributes the lateral load to the different columns. So it starts out on the outer cladding, then it gets that gets distributed to the floor slab, or sometimes there might be a beam on the outside, and maybe it could be distributed by beams instead of floor slab. But a very simple model could assume that it's just going directly to the floor slab. Then the floor slab delivers the lateral load to the columns, and then the columns carry it to the foundation. So if I were to look at something like the window here, the window is in bending like this. The window could be treated as something that's simply supported, and it would be bending like this, kind of in this direction. What about the columns? What kind of load will the wind be producing on the columns? It's going to be producing two types of internal forces. What? Shear and moment. Because think about it. This load, if I look at a column, and I'm treating this as an unbraced frame, like we don't have substantial bracing, so we'll talk about lateral load resisting systems later in the semester, but I just want to give a brief introduction here. You can also have this would be like a braced frame where the columns are directly resisting lateral load and bending rather than something like, say, a braced frame. But so you'd have these loads here would be the point loads coming in from the slab. So this, again, all of the windows end up gathering load, all the brickwork, whatever it may be, gathers lateral load. That gets distributed into the floor slabs, into this floor slab, and or in this case, it would be directly to the foundation. And then the floor slabs or the floor beams, in certain cases, would distribute it directly to the columns. And the columns then would have a tendency to kind of bend like this if they were free to. They'd have a tendency to bend like that. And so the columns will be in both shear, a shearing force, and in moment. So in this case, the columns are actually acting as cantilevered beams. They not only have to support the vertical loads, so we can see here one of the reasons that column design is so tricky and so critical. Columns need to carry quite a bit of different types of loading. They will generally have to carry, they'll always have to carry vertical load from the distributed vertical loads of dead load, live load, self-weight, etc. They'll always have those dead loads, the big vertical dead loads. They'll always have those big vertical loads, but they'll also often have to carry lateral loads from wind, from seismic, etc. So column design is always very critical and very tricky because of this. Okay, but that's the basic idea of load path. All right, so we've seen vertical load path, we've seen horizontal load path, we've seen one-way loading, we've seen two-way loading. Any questions on this idea of load path? Okay, all right, I think that'll do it for this video. I just want to show you the basic principle for how load gathers, how load distributes in structures. We will talk about this more later in the semester when we look at especially diaphragm action, braced versus unbraced frames. That should serve as a good introduction to some of this material. All right, that'll do it. Thank you for watching, and as always, thank you.